Hello, my name is Alexander Panov. I'm from Skobeltsyn Institute of Nuclear Physics, Russia. My talk will be about 10 TeV of cosmic rays measured with the Nuclear Space Experiment. The nuclear mission was designed to measure cosmic ray particles from the energy approximately about 1 TeV to 1 PeV with individual resolution of charge. The apparatus was launched in 2015 to synchronous orbit with inclination about 97 degrees and with altitude about 500 kilometers. Two methods of energy measurement were implemented on board of the experiment. First is usual ionization calorimeter, and second is new kinematic method, CLEM. The CLEM method is based on the fact that the number of secondary particles with high perceived rapidity after the first interaction in the target increases logarithmically along the increasing of the primary energy of particles. Some special parameter S was developed to measure the energy of the primary particles, which is related to the number of past secondary particles. The spectra of main abundant nuclei were measured with the experiment. The natural parameter of measuring the spectra is the energy per particle, but the charge of each particle is known. Therefore, we easily may convert this energy to the magnetic rigidity. And it was discovered in 2018 that all nuclei of the cosmic rays, like protons, helium, heavy nuclei, have the same features in the spectra, like Ne near the magnetic rigidity about 10 TeV. You can see this feature in different components of the spectra and in the all nuclear spectra. But this spectra was obtained by in event procedure of obtaining the energy, and there is no energy deconvolution in the spectra. But the apparatus function in both in the CLEM and in the ionization calorimeter is rather wide. Therefore, some deconvolution of the spectra is needed. Now I represented the results of energy deconvolution for the energy obtained in CLEM method. It is very important because the CLEM method has the geometric factor 6 times higher than the method of ionization calorimeter in the nuclear experiment. In these diagrams, you see some connection of primary energy of the particles with the CLEM parameter S simulated in the computer. You see some strong correlations of S and E in E, and it permits to establish some connections of E with S in some power-like shape. A in B is the parameter that can be obtained from these diagrams. Now, this relation was used in event-by-event reconstruction of energy from the parameter S of CLEM. Now about deconvolution. Deconvolution was obtained with the equation like this, where M is the number of events of some energy being G of the of spectrum without deconvolution, and this is the spectrum with deconvolution, the result of this procedure. P is the probability matrix, and Pig is the probability to get the energy of the true spectrum in beam number I have an energy of the original spectrum in beam number G. All these probabilities is known to unit in each line of this matrix. This matrix were calculated by Monte Carlo method. First, for power-like spectrum with spectral index gamma equal to minus 20.6. Then, for the first result of the convolution, then for the second result of this deconvolution with a number of iterations. Actually, 3 iterations were used for all spectra, since 4th, 5th, etc. iterations produce almost same results. In this picture, you can see the results of this work. You can see the spectra in terms of magnetic rigidities for different nuclei, for different nuclear groups, for all particles, and you can see that in the spectra with deconvolution, the same feature like an E near the magnetic rigidity near 10 TeV, but you can see that the position of the knee, if a bit different than was obtained without the convolution. Without the convolution, it was about 10 TeV, but in this spectra, you see rather 20 to 30 TeV. Therefore, there was some systematic uncertainty in the determination of the position of this knee with the method, with event by event reconstruction of the energy. In this picture, you can see the spectra of all particles or of all nuclear experiment obtained with the same deconvolution procedure, and you can see that the spectrum of nuclear experiment represent the spectrum obtained with Hawke ground experiment. Rather reasonable. The spectrum is rational agreement with each other. Now some words about the systematics of the spectra obtained by reconstruction with deconvolution. There are a number of main different sources of the systematics, as the main sources are the following. First, it is uncertainty of the spectral index gamma used in reconstruction of A and B parameters to reconstruct the single energies. This uncertainty produces about 16% in absolute intensity of all spectra. Then there are fluctuations during iterations. And these fluctuations produce about 20% of uncertainty of absolute intensity in the statistically reliable part of the spectrum, and about 50% at high energy end of the spectrum. Then there is some uncertainty related to simulation connected to the simulations of the spectrometer. Simulations of the spectrometer with different systems show that this uncertainty is about 6% in the measurement of energy. And finally, there exists uncertainty of various selection criteria to select events to collect them to construct a spectra. This uncertainty we estimate like about 20% of absolute intensity. Finally, this is a picture represents our systematics. The systematic errors is approximately the same for different nuclei. For spectra of different nuclei, therefore, I can show the systematics only for the spectrum of protons. These arrow bars show the systematics in absolute intensity of the spectra. Is in the high statistics part of the spectra, it is about 35%. There is 60% near the high energy part of the spectrum. Also, there is some uncertainty in the position of the knee related to uncertainties of the simulation systems. The slope of the spectrum at high statistically part is rather stable, but the slope at the low statistical part of the spectrum may change a bit to high and up position. But the existence of the 10 TeV knee is stable against the systematic uncertainties, but the systematics of the position of the knee is represented by the factor about 2. Also, I want to say some words about the physical meaning of this knee. This knee takes place at the same position in a spectra of different nuclei. Therefore, it lacks like energy break in some special source of cosmic rays, and it will be shown in our future works that this source actually may be a single nearby supernova explosion. Thank you for attention.